Hello, welcome back to part two of this lecture. Uh, in the previous part, we discussed about covariance and correlation. Uh, this section is about linear regression. As I mentioned at the end of the last lecture, here we are not looking at the usual regression analysis that we do when you have a sample of XY points. What we discuss here is a theoretical idea uh, about the linear regression between two random variables, between two jointly distributed random variables, X and Y. Uh, so we are going to look at something called least squares regression function. So to define what we mean by least squares linear regression function between two random variables, let capital X and capital Y be random variables such that the expected value of X square is finite and expected value of Y square is finite, and the variance of X is greater than zero. That means variance of X is not equal to zero. And let curly X denote the set of possible values of capital X. Then, under this setting, the least squares linear regression function of y on x is a function defined, function L, say simple L, defined from this curly x2 set of real numbers, defined so that L of x is equal to alpha plus beta x for a x in the curly x, where these alpha and beta are respectively the values of A and B that minimize this expectation here. Expected value of y minus A minus bx square. Right. So that is a particular function of x, where x, simple x, is a possible values of possible value of capital X. And alpha and beta are two values that minimize a particular squared expected value. Well, expected value of a squared term. So what is this? Y minus A minus bx square. So if you, for example, consider a straight line A plus bx, so y minus A minus bx can be considered as the distance between y and A plus bx. So we are considering the values of A and B that gives you the minimum expected value of the squared differences between y and A plus bx. So you can notice that y is a random variable, x is a random variable, therefore this whole thing is a random variable, therefore we can talk about the expected value of that. We look at the minimum of this quantity over all possible pairs of AB, where A is a real number and B is a real number. Once you get that A and B, once you find out the A, B satisfying this, minimizing this condition, minimizing this expected value, we call those A and B alpha and beta. Right. So then we have this function. Now in this one, L1, Lx is alpha plus beta x is just a mathematical expression here as a function of mathematical function of x. But if you consider that quantity as a function of capital X, you get this L capital X is equal to alpha plus beta X, and now it is a random variable. That random variable is also denoted as y hat L, because that is what we use as an estimator for y for a given for y as a function of x. So we use this thing as an estimator for y for a given x. Therefore, it's called a linear predictor of y. Linear predictor of y. So it is not, that is why we have a different name than estimate. Estimator usually we talk about for a parameter. In this case, y is not a parameter, y is a random variable. So in the usual uh, way of using the words, estimator is not a good word here, even though we are kind of estimating y, but it is in the classical sense, it's not an estimator. So that's why we call it a linear predictor, right? But it's a random variable. This quantity is a random variable. Hat denotes, usually we use hat to denote estimate or estimator, but we use the same idea here with to denote the predictor. So the quantity that we are minimizing here is a function of A and B. Let's call it Q of AB. That quantity is called the least squares criterion. Least squares criterion, right? So we are looking at some squares and we want to minimize it. Least, find out the value of AB that gives you the minimum, the least value, the smallest value for this quantity. So that's why least square criterion. That is the criterion that we minimize. The minimizing values of alpha and beta are referred to as the population least squares regression coefficients. So the values of AB that minimizes this quantity are denoted as alpha and beta. They are called population least square regression coefficients. Alpha is the intercept and beta is the slope. So this function that we considered earlier is the same as the least squares linear regression function. So it's just a mathematical function. It's referred to as the least squares linear regression function of y on x. So this random variable we just mentioned is referred to as the least squares linear predictor of y based on x. So let's briefly discuss how to derive alpha and beta, how to get alpha and beta. Right, so let's consider this as QAB, a function of some AB. So if I expand this term inside this and then take the expected value, I get this expression here, right? So first expand this quantity. So expected value is outside. And then just apply the property of expected value, right? Expected value of this random variable, then minus 2a times expected value of y, minus 2b times expected value of x times y, and so on. Now we want to minimize this quantity with respect to a and b. So first take the derivative, partial derivative with respect to a and equate to 0. That gives us this expression here. Right? A plus b, expected value of x is equal to expected value of y. That is one expression that we get. And we will also differentiate, take the partial derivative of q with respect to b and equate to 0. That gives us this expression here. So both contain a and b. The previous expression contains a and b. This contains a and b. So if we solve these two values, we get some values for A and B, that point, AB point, can be considered as the stationary point of this Q function, stationary point. Then we have to check whether it is a minimum or a maximum or a saddle point by looking at the required condition the for that, right? To check whether it's a minimum or maximum or saddle point. So from this, when you solve these two equations, we get value A as expected value of y minus B times expected value of x. And if you substitute this A into the previous equation and solve for B, you get this expression. UB is equal to this thing divided by this quantity. And that is the value of B with respect to at the stationary point. And later on, we actually have to verify that at the point AB satisfying this, and this is actually the minimum point. We can show that. Therefore, I have actually taken this B value coming from this equation as beta. So beta is equal to this quantity divided by this one. And where this one is actually the variance of x, expected value of x square minus expected value of x, whole thing by the variance of x. So this is the expression that we get for beta. When I substitute that for B in this one, we get alpha corresponding alpha. Therefore, alpha is equal to expected value of y minus beta times expected value of x. So that is this expression. Now, to verify that alpha beta is the minimum point, we have to consider the Hessian matrix. Right? Hessian matrix is the second derivative matrix of our Q function. So this is the second derivative with respect to A. This is the second derivative with respect to A and B. This is the second derivative with respect to A and B. And this is the second derivative with respect to B. You can take every term has a 2 as a product. So you can take that out. Right. So the first leading principal minor, that is actually going to be 2, is positive here. And the determinant of this Hessian matrix is positive. Right, we get this expression, and this is actually the variance. So variance is positive for the random variable x. Right, x is not a constant here, therefore we can that implies that this alpha beta point is actually the minimum point of QAB function. So therefore, the unique least square solution, right, alpha beta is given by alpha is equal to mu y minus beta x, where beta is given by covariance xy divided by variance of x. Right. So here beta, this quantity is covariance, this is the variance. Now, if in addition, variance y is also greater than 0, that means variance y is not equal to 0, then beta can be written as rho times, because this beta here, it can be written as rho times sigma y divided by sigma x. Because we can write down rho is equal to, or covariance is equal to rho times sigma x times sigma y. So one sigma y will be cancelled out with the sigma y square here. So therefore you get this expression. Right? Beta is equal to rho times sigma y divided by sigma x, where rho is the Pearson correlation coefficient, theoretical Pearson correlation coefficient, or the population Pearson correlation coefficient. So this expression actually has a good implication. Remember, I told you that earlier. Rho is a measure of the linear association between x and y. And now we can see there is a direct relationship between rho and this beta, where beta is the slope of the line that we are considering here as a function of x. So this quantity is always positive, this quantity is always positive. So therefore the sign of beta is the same as the sign of rho. So that means if the slope beta in the least squares regression line is positive, then rho is also positive. If beta is negative, then rho is also negative. And uh, this expression is valid only for that linear regression line. So therefore, rho directly can be considered as an interpretation, can be given in terms of the linear relationship only. Right? So that is where uh, the interpretation that rho is a measure of the linear relationship comes, because there's a direct relationship between the slope of a linear regression function and uh, the correlation coefficient rho. So the consequences of the least square solution we got earlier our normal equation. These are called normal equations. These are the equations that we solved to find out alpha and beta, right? So that means at uh, the first derivative when a, b is equal to alpha, beta, we get this expression in terms of alpha and beta. And similarly, the first derivative with respect to beta, evaluated alpha and beta will be equal to this thing, right? These are called normal equations. These two equations are called normal equations. Now, this one you can write down as this expression y expected value of y minus alpha minus beta is equal to 0. You can easily see that, right? This is equivalent to this. And similarly, this one, this expression can be written as this expression, expected value of x times y minus alpha minus beta is equal to 0. So those are two important results. Y minus alpha minus beta is equal to 0, expected value. And then expected value x times this quantity is also 0. Now let us denote this alpha plus beta x line. That is the line that minimizes the sum of squares of uh, differences between y and a plus bx. And let us denote it by y hat L. Right? As I mentioned, that is the predictor, linear predictor, with the least squares linear predictor that we have already derived. And define the corresponding linear predictor error, right? Also called the population regression residual, y minus this quantity. This is the predictor, y is the original random variable. So the difference between those two is called the linear prediction error. So that's also a random variable. And because it's also called residual, right? Population regression residual, I have denoted it by R. Right? Some people denote it by epsilon and call it error. But I like to call it residual y minus y hat x. So that is equal to y minus alpha minus beta x. Now, here, this equation, so this is actually expected value of now the residual. So expected value of residual, L denotes here the linear function, right? Linearity. So expected value of the population regression residual should be equal to 0. Right? So if you get the least squares regression line, then corresponding to that, there is a residual, and that residual has expected value equal to 0. And expected value of x times RL is also equal to 0. That's coming from this expression here, this x and then this RL. So therefore, if you look at the covariance between x and RL, x is the usually in usual setting, this is called the explanatory variable. RL is the residual. So it is equal to expected value of the product of these two minus expected value of x times expected value of RL. So we have seen that this term is 0 and this term is also 0. Therefore, covariance between x and RL is equal to 0. So that implies that x and RL are uncorrelated. Uncorrelated. Right. So if you compare with the sample regression situation, you remember usually we plot the residuals coming from our model using the data versus x. Right. So if x and r will theoretically are uncorrelated, we expect when we plot r residuals versus x, we expect there to be no pattern, right? Especially not to see any correlation there, uncorrelated. So that's why we say usually we expect in the residual plot to have no pattern. Furthermore, expected value of the predictor is the same as the expected value of y. So you originally have a random variable. Now, expected value of predictor is also the same as expected value of y. That is also a good property. Otherwise, if the predictor on average is quite different from the average of y, it's not a good property of the predictor. Right? But here, predictor and y are the same on average. And the covariance between the predictor and the residual is also 0, because covariance between this thing, we can see that is equal to beta times the covariance between x and RL, because we know that y hat is equal to alpha plus beta x. So if you replace here by alpha plus beta x, using the properties of the covariance, you can easily see this. But because covariance between x and RL is equal to 0, this is also 0. So that is, you can compare it with again the sample analysis, usual regression analysis using data. Usually we plot residuals versus the fitted values. Right, corresponding random variable is here y hat L. So because theoretically y hat L and R residuals are uncorrelated, again, when you plot the residuals versus the fitted values, you expect they are to have no pattern, right? No correlation. So that is again gives you that again gives you a justification for why we do not expect any pattern when you plot the residuals versus the fitted values if the assumed linear model is a suitable model. Right. Thus, the linear predictor error has mean 0 and it's uncorrelated with both x and the least squares linear predictor. These uncorrelatedness properties do not in general imply independence. Right. So that is an important thing, right? It doesn't say that X and RL are independent, or it doesn't say that Y hat and RL are independent. They just say they are uncorrelated. Of course, X and Y were, for example, jointly bivariate, normal. In that kind of situations, independence may occur, right? But in general, covariance equal to zero doesn't imply independence. So if you look at further consequences, actually, I have already mentioned this. Beta is equal to rho times sigma y over sigma x. Therefore, beta and rho have the same sign. The interpretation of rho as a unitary measure of the direction and the strength of the linear association follows naturally from its relationship with the population regression slope. Right? Unitariness comes from the way that we have calculating it, rho, right? Rho is equal to covariance divided by this product of standard deviation. So units will cancel out, right? Uh, so the direction or the relationship, if the direction is positive, then rho is positive. If the direction is negative, rho is negative. So as I mentioned earlier, the fact that it is giving you the measure of the linear association, measure of the strength of the linear association comes from this particular thing, the direct relationship between beta, the slope of the regression line, and rho. If rho is equal to zero, then beta is equal to zero. In that case, Lx will be equal to mu y, and the predictor will be equal to mu y. Therefore, right, Lx will be equal to mu y, and predictor also will be equal to mu y. So that means if rho is equal to zero, then the predictor is a horizontal line. It's a constant. The predictor doesn't change with x. So that means if there is no relationship, no correlation between x and y, then the predictor will be just equal to, actually in this case, the mean of y, right? So that tells you, for example, if you're predicting y when x and y are not correlated, the best prediction is the mean of y. The best prediction is mean of y. The best prediction means the prediction that gives you minimum squared uh, difference between the y and the predictor. If x and y are independent, then the covariance is zero, right? And hence beta equal to zero. So now we are talking about the other way around. If x and y are independent, right? Therefore, independence implies a flat square linear regression. Right? So if the correlation equal to zero, that also implies a flat regression line. And in particular, if x and y are independent also, then we have a flat squares regression line. If the least squares regression line is non-flat, then beta is not equal to zero, and consequently covariance is not equal to zero. Therefore, a non-flat least squares regression line implies that x and y are dependent. They are dependent. Otherwise, if they were independent, then correlation covariance has to be zero. But if the covariance is not equal to zero, that implies x and y are dependent. Remember, covariance equal to zero does not imply they are independent. But covariance not equal to zero implies that x and y are dependent, not independent. Right? A flat least squares regression line implies only that covariance is equal to zero. It does not imply that x and y are independent. a nonlinear dependence may still exist between x and y. Now we are going to look at something that you may be familiar in usual regression analysis, something called variance decomposition. The same idea exists in the theoretical setting also for the population. Right? Variance decomposition and linear coefficient of determination. So if you remember the usual regression analysis, there also we talk about something called coefficient of determination, usually denoted by R square. Here we are going to look at the population analog of that quantity. So recall that we can write down y as y hat plus RL because we define RL to be y minus y hat L. So y is equal to y hat plus RL. So y hat is equal to alpha plus beta x, right? And therefore you can have this part where y hat is equal to this one. So there and RL is equal to y minus y hat. So let's look at the variance of y. Variance of y is equal to variance of y hat plus RL. And that is equal to variance of this quantity plus variance of this quantity plus twice the covariance between this and this. But few minutes ago, we showed that y hat and RL covariance is between those two is equal to 0. And therefore, this term disappears. And therefore, variance of y is equal to variance of y hat L, that is the linear predictor, plus variance of the residual. So that is what you mean by the decomposition. Variance of y can be decomposed into two parts. Now, these two quantities have two particular names. The quantities y hat L and variance of y hat L and variance of RL are referred to as, respectively, variance explained and variance unexplained by the least squares linear regression of y on x. So this is the variance explained by the least squares linear regression. This is the variance unexplained by the least squares regression line. Now, if variance of y is greater than 0, then since beta is equal to rho times sigma y divided by sigma x, we can write down from the previous expression here, variance of y hat L, right? This one. We are looking at variance of y hat L, which is equal to variance of alpha plus beta x. So alpha is a constant. So variance of constant times x, this will be beta square variance of x. Now we substitute from beta here, we get this expression, variance of y hat L is equal to rho square times sigma square y. Right. So the variance of the predictor is equal to rho square times variance of y. Remember, rho square, rho is always between -1 and +1. Right? So rho square will be always less than 1, greater than 0. Right? So it's a decimal number. So what does it tell you? Variance of y hat L is going to be smaller than variance of y because variance of y is going to be multiplied by a decimal number. Variance of y hat predictor. So that's a good thing, right? A predictor has a smaller variance than the variance of y itself. Now, let's look at this quantity, variance of y hat divided by variance of y. Right? So remember, I told you that variance of y hat is going to be smaller than variance of y always. Right? So therefore, this ratio is going to be always between 0 and 1. Right? The population linear coefficient of determination. That is what this quantity is called. That is the ratio of explained variation divided by the total variation. This is the variation of y explained by the least squares regression. And this is the variation of y without explaining by x, that is the original variation. So the ratio is equal to rho square, right? Rho square. Rho is the Pearson correlation coefficient theoretically. So in this case, when you are looking at the linear regression, the linear coefficient of determination is actually equal to the square of the Pearson correlation coefficient. So therefore, the R square L, which is the proportion of the variance of y accounted for by its least squares regression on x, is equal to this rho square, right? So R square L is interpreted as the proportion of the variation of y accounted for by its least squares regression line. So this is the variation of the least squares regression line, and this is the original variation. So that's why we call it the proportion of variance of y accounted for. But here the word accounted for, okay. Here the word accounted for refers to linear predictive variation and does not imply causal relationship. Right? Accounted for doesn't mean that it is causing the reduction of this variable necessarily. Right? It is not a causal relationship. That means that we usually mention in regression analysis also, right? Regression doesn't imply a causal relationship. That only implies there is some kind of association. The same idea here, right? The reduction of variation is not caused by x, but it is explained, right? We can explain certain amount of variation in y by x because there is some association between x and y, right? Okay. Now we are going to look at some optimality of this predictor, linear predictor. Optimality of the conditional mean and the least squares predictor, right? So these two quantities actually, one is conditional mean, the other one is the least square predictor. Both are optimal in some sense. So we are going to look at these two views of optimality. And we will see in some situations, both are the same, right? So let us denote by the expected value of y given x as mx, right? So we know that expected value of y given x is always a function of x, right? So let's denote it by mx. And also define u to be y minus this fx, mx. So u is equal to y minus the conditional y given x. Right. Then we can prove that expected value of u given x is equal to 0, right? You just take the expected value of u given x, so that is the same as expected value of y minus mx given x, expected value of y given x minus mx, and this is mx, therefore this is equal to 0. Now, let us take gx to be any predictor, not necessarily the linear predictor that we already have, let's take gx to be any predictor satisfying this condition. Expected value of gx square is finite. And let us consider y minus gx. So that can be written as y is equal to u plus mx minus gx, and y minus gx is equal to this one. So let's now consider the expected value of this quantity, squared of this quantity, y minus gx. Y is the original variable, and gx is the linear predictor that any predictor that we are considering, not necessarily linear, any predictor, right? It can be some other predictor like e to the power x, log x, whatever, right? So expected value of y minus gx square. So we are considering actually expected squared difference between the variable and the predictor. And if you expand this is going to be expected value you take in from this one. You can easily see that is equal to this expression here. Expected value of square of this, expected value of square of this, and then twice the expected value of this times this. Right. Now, we can find out this expression here, but we are interested in finding actually this quantity. We are going to keep this one, but we want to look at this quantity. Here you have a product of two quantities now. Therefore, when you are considering expected value of that, we know we can get that expected value by conditioning on x, because that quantity itself is this quantity itself is a function of x. So therefore, the expected value of this quantity u times this function is equal to expected value of this thing given x. Right? So when the x is given, this part, which is a function of x, can be considered as a constant. Therefore, you can take it out of this expected value, and then you'll have expected value of u here given x. Right? Given x, this part can be considered as a constant now. So now you have expected value of this quantity times the expected value of u given x. And that is equal to 0 because expected value of u given x is 0. We showed it here. Expected value of u given x is equal to 0. So this term here, therefore, disappears or vanishes. And therefore, expected value of y minus gx square is equal to expected value of u square plus this quantity. Right? So consequently, we can get this one. Now, if you look at this quantity, this is the expected value of a squared random variable. Therefore, that quantity is always greater than or equal to 0. So that implies that this quantity here is greater than or equal to this quantity. Right? Where gx is any predictor, mx is actually the expected value of y given x. Right? So this follows expected value of y minus x mx square is less than or equal to this quantity. Equality happens if and only if gx is equal to mx with probability 1. So that means for all x, not necessarily all x, but for those x's whose probability is equal to 1. Right? Thus, mx is equal to expected value of y given x is the unique minimum mean squared error, right? So in that case, we are looking at the mean squared error, right? Mean squared. Mean is this one. This quantity is the error. So this whole thing is the squared error. Mean squared error predictor of y among all square integrable functions of x up to events of probability 0. Right? So therefore, this mx is one type of optimal predictor of y. Mx, which is the conditional expectation of y given x, is the unique minimum mean squared error predictor of y. Right? So that can be considered as a predictor. But that is the unique minimum mean squared error predictor of y among all square integrable functions of x. Square integrable functions means the integration of the squared function is finite. Now let us consider a subset of this gx that we considered, right? We consider here gx to be any function, any predictor. So we showed one thing. Out of all gx predictors that we can consider, mx is the minimum mean squared error predictor. Now let us consider the linear predictors like this. So let us call it a subset of the class of gx functions denoted by gabx because it's a linear predictor here. And denote y hat l as the least squares predictor that we obtained earlier. So that is y hat. Right? We already have alpha plus beta. So this is the least squares predictor. Be the least squares linear predictor. And let RL be the residual coming from the least squares linear predictor. Excuse me. We have already shown that expected value of RL is equal to 0 and expected value of X times RL is equal to 0. We already showed those things earlier. So if you now consider again expected value of y minus gx square, which is equal to this thing, and we showed that the product term disappears because this quantity is positive. We can see that expected value of y minus mx square is less than or equal to expected value of y minus gx square. So equality holds if and only if gx is equal to mx. Actually, this is a previous one. I have gone to the previous one. So by a mistake, this is where I was, right? Yeah. So this is, here I'm considering the linear least squares predictor, right? So for any a b square, y minus a minus bx can be written as this, right? So earlier we were considering now a restricted class here, right? So y minus a minus bx, let's consider that difference. Y is the random variable. Y, this is the predictor that we are considering, a particular class, a member in the particular class of linear predictors. So you can write down it as this, right? So just add, uh, because RL is equal to this quantity. If you substitute y by RL and in terms of alpha and beta, then RL plus alpha plus beta is equal to y, and then you have minus a minus b times x, right? So if you consider the square of this thing and take the expected value, you will get this expression, expected value of RL square, and then expected value of this quantity square, and then a product term here. And then we can show that the product expected value of this term is actually equal to 0, because you can show that this is equal to a constant times expected value of RL, and then another constant times expected value of X times RL. So therefore both are 0, therefore this one is 0. So therefore you can see that this is equal to this quantity plus this quantity. But this one is a positive quantity because it's the expected value of the square term. So that tells you that this quantity is greater than or equal to expected value of RL square. So what does it tell you? Uh, Thus y hat L equal to alpha plus beta x is the minimum mean squared error predictor within the class of predictors alpha and beta. Right. So this is the expected value when you of similar term when you have alpha and beta here, right? So y minus alpha minus beta x square expected value of this quantity. So that quantity is always less than or equal to the square difference between y and the predictor for any other linear predictor. So therefore, it tells you that y hat L equal to alpha plus beta x gives you the minimum mean squared error. This is the minimum squared error predictor within the class of predictors A plus Bx. So therefore, we have another optimal condition that is within the predictors of the form A plus Bx, least squares predictor is the gives you the minimum mean squared error among all those linear predictors. So finally, applying equation 13 with gx equal to lx, right? 13 is equal to this expression here. Now, if I replace this gx by our least squares predictor, then we have expected value of y minus lx square is equal to this expression. So if mx is equal to lx, right? Right now we can write down this thing in terms of mx and lx both, right? Where mx is the conditional mean of y given x. This is the least squares linear predictor. So if mx is equal to lx, this term will be 0. In that case, the least squares linear predictor is optimal among all functions of x. Right. Earlier we showed that mx is optimal in terms of the squared error. It gives you the minimum squared error among all the functions if you consider all the predictors. So if mx is equal to lx, then the least squares predictor is actually the optimal predictor among all functions of x. So conditional expectation of y is the optimal predictor among all functions of x. There are some situations where the expected value of y given x will be equal to the least squares predictor. In that case, least squares predictor is the best or optimal predictor among all predictors of y as a function of x. If mx is not equal to lx, always, that means if mx is equal to lx maybe at some time, but not with probability 0, not with probability 1, I made a mistake, right? That means if the probability that mx not equal to lx is some positive value, in that case, expected value of y minus mx square will be less than expected value of y minus lx. So in that case, if these are not the same, of course, the conditional expectation is better than the least square. So, right, because the squared error, expected squared error for the conditional mean is less than the expected squared error for the least squares regression line. Right? So that happens if mx is not equal to lx. In this case, the least squares linear predictor is optimal only within the affine class and is not optimal among all functions. The affine class means the linear functions class of linear functions. In general, mx and alpha plus beta x are different. Mx is the conditional mean, alpha plus beta x is the least squares predictor. They are in general different. They coincide whenever the conditional mean is linear. So if the conditional mean is linear function of x, in that case, least squares predictor and conditional mean are the same. In that case, least squares predictor is the best among all possible predictors of y as a function of x. Okay, now let us look at one or two examples. Suppose that x and y follow a bivariate normal distribution with variance x greater than 0. Show that the conditional mean expected value of y given x coincides with the least squares regression line of y given x. So this is a special case actually, where the conditional mean of y given x is actually going to be the same as the least squares regression of y on x. So if x and y are bivariate, have a bivariate normal distribution, this is the way that usually we write down the notation x and y bivariate normal with this mean vector and this variance covariance matrix. This is the variance of x, this is the variance of y, and these two are the same. That is the covariance between x and y. For a bivariate normal distribution, the conditional distribution of y given x is also normal. We can prove it using, we can get the expression. It's a long expression for the density function of, joint density function of x and y. And you have to divide that by the marginal density function of x. Marginal density function of x is also normal. So if you simplify that, you can show that y given x equal to simple x, y given capital X equal to simple x is also normal as a normal distribution with this mean and this variance. So therefore the conditional mean is equal to this quantity, that is mu y plus rho times sigma y divided by sigma x, x minus mu x. That is the conditional mean in this case. And you can see that that's actually a linear function of x. Right? This is a linear function of x. Let's look at the least squares regression line in this case. That is equal to alpha plus beta x with beta equal to this expression. Covariance between x and y divided by variance x. So covariance here is equal to this expression divided by variance given by this one. So beta is equal to this expression. And alpha is therefore mu y minus beta mu x. So that is this one. So therefore, the least squares regression line, alpha plus beta x, will be this expression here when you substitute into alpha and beta. And this is the same as this expression here. So therefore, we see that the least squares regression line in this case is the same as the expected value of y given x. Thus, for the bivariate normal distribution, the conditional mean expected value of y given x and the least squares regression line of y on x are identical. Right. Let's look at another example. Find the conditional mean for a uniform distribution on the rectangle ABC where vertices A, B, C with given these 0, 0, 1, 2 and 1, 0. Prove that the conditional mean and the linear regression are the same for the uniform distribution on the rectangle. So this is another special case where the conditional mean of y given x and the least squares regression line of y on x are the same. We have already looked at this example in a previous video where we found out conditional mean and everything. So therefore, I'm going to directly use those results here. So here, this function, uniform distribution is defined on a triangle where that triangle is given by these xy coordinates, x between 0 and 1, y is between 0 and 2x. So in that case, the area of the triangle is equal to 1. So therefore, since xy is uniformly distributed on T, its joint density function has to be 1 here. So that the volume under the the joint density over this T has to be 1. So therefore the joint density is 1 in this particular region. Right? So if you find out the marginal density is given by fx equal to 2x, where x is between 0 and 1. So therefore the conditional density function of y is given by the marginal density divided by the, joint density divided by the marginal density. Therefore it's going to be 1 over 2x. Therefore the y given x is uniform, right? Because y is between, for a given x, in that case, x is fixed, right? We are looking at the conditional density of y given x is equal to simple x. So in this case, x is fixed. So therefore, when x is between 0 and 2x, where 2x is a fixed value, therefore this is a uniform distribution. We have looked at this example previously, as I mentioned. So therefore, y given x is uniform between 0 to x, and therefore the conditional mean either you can directly you can obtain by the definition like this, or you can directly use the known properties of uniform. We know the mean of a uniform distribution is the if uniform is in a b interval, then mean is a plus b divided by 2. So similarly here the mean therefore should be 0 plus 2x divided by 2, that is x. Right. So that is the expected value of y given x. So you can see that's a linear function of x itself. Right. Now we will also find out the least squares regression line alpha plus beta x. So in order to find out that one, we need to find out alpha and beta separately, where beta is equal to the covariance xy divided by variance of y, and alpha is given by this expression. So in order to, we can get expected value of x and expected value of y. We know that how to get those things. Once you know the marginal density, therefore you can get this expression, expected value of x, very easily. Right. So I'm not going to explain those things. Expected value of x and expected value of y both are the same in this case, because it's symmetric in the sense that we are looking at the support is a symmetric triangle, as well as the density function is uniform. Therefore, expected value of x and expected value of y should be the same. And similarly, now expected value of x square you can find out by just integrating. We know how to do it now. Therefore, I'm going to explain that. And we need the expected value of x times y also. We can obtain. We have already obtained these things in a previous example. So once you know the expected value of x square and expected value of x, we can get the variance. So once you know the variance of x, variance of y, or those things, we can get the covariance, and we can get the beta also, right? So covariance is expected value of x times y minus expected x times expected value of y, and we get this answer. So beta x is equal to covariance between the variance of x, that is equal to 1 in this case. Alpha is equal to 0. So therefore, the least squares regression line is just alpha plus beta x, which is equal to x. So we saw that expected value of y given x is equal to x. The least squares regression line is also x. So therefore, they are the same, right? That means expected value of y given x, which is the best predictor among all predictors, is the same as the least squares regression predictor in this case, x, right? So the conditional mean and the least squares regression line are the same for the uniform distribution on the given rectangle. So those are two special examples where the expected value of y given x, which is the best predictor among all predictors, is the same as these two examples, they're the same as the linear least squares regression predictor. Uh, let's look at another example and let's see whether those two predictors are said the same or not in this case. We have looked at this example also in a previous situation when we were calculating expected values, conditional distributions, and so on. So I'll be using some of those results also directly. Let's consider this joint density function. This is actually I have described this as a certain beta function actually, certain beta function. The marginal and conditional densities are given by these two expressions here, and this is also a no, it's not a beta distribution. Well, yeah, it is a beta distribution. Yeah, and this is also a beta distribution. Right. This is the conditional distribution. Right. So therefore, expected value of y given x, we can easily obtain from this expression, considering x as fixed, and then variance of y and variance of standard deviation of y, like this expressions. And therefore, for the same distribution, we can also find out expected value of x, variance of x, expected value of x times y, and covariance, right? So expected value of y given x, that is one thing that we are interested in, that is 2 over 3, 1 minus x. So that is, you can see that that's a linear function of x. That is a linear function of x. And let's now look at the least squares regression line. That is, we have to calculate beta covariance divided by the variance of x. So that is this number, alpha is equal to mu y minus beta times mu x. You get this expression. So therefore, YL is equal to this one. That is the least squares regression predictor. And expected value of y 2, 3, 1 minus x. So this is the same as this. And actually it should be, because remember I mentioned that if the expected value of y given x is a linear function of x, in that case, expected value of y given x and the least squares predictor are the same. Right? So this is another example where both of those predictors are the same. Right? In addition, here I have just calculated the rho. Rho is equal to negative 2 over 3. R square L, in this case, is the coefficient of multiple determination, that is 4 over 9. Right. Okay. So that is the end of that section. Right. We discussed about the least squares regression predictor of y on x. And also we showed that expected value of y given x is the best predictor of y in terms of x among all predictors. When that predictor is a linear function, that predictor coincides with the least squares regression predictor. Okay. So in the next part, we will look at few other topics just to fill the gaps, right? We have already in some other second chapter, actually, I have mentioned briefly about order statistics. In this section, in the next part, I will derive distributions of the minimum and the maximum and the rth order statistic. And then we will also look at a way to get the distribution of any one-to-one transformation, right? So that is not actually coming under multivariate, univariate problems, but that is important for us to later discuss about transformation from x1, x2 to y1, y2, right? Bivariate transformations, right? So therefore, I will briefly talk about this one also for the univariate case, and then we will discuss about how to find out the distribution of a bivariate transformation, right? So that will be the next discussion in part 3.